Alright, so let's look at the final section of the mock exam, the multiple choice questions. So the first one is looking at which of these is a possible unit of impulse. So the first thing for this is you have to know that an impulse is a change in momentum. So an impulse has the same unit as momentum, and momentum is mass times velocity, so it would be kilograms meters per second, which is one of those options. You sometimes also see that as Newton seconds as well, so that could have been a possible one, but that's not there. Kilogram meters per second is. Okay, so then we've got next one. The audible range of a girl's hearing is 30 Hz to 16,500 Hz. The speed of sound in air is 330 meters per second. What is the shortest wavelength of sound in air which the girl can hear? So the first thing in your mind you need to go, shortest wavelength, highest frequency. You should know those two things are inversely proportional at the same speed. So you pick the 16,500 and then rearrange the wave equation, so you should have velocity divided by frequency gives you wavelength, and that gives you option C there. You didn't even need to calculate it. Which one of the following types of wave cannot be polarized? So you should know that for polarization to occur, you have to be a transverse wave. The first three options are all electromagnetic, which are transverse type, leaving D that must be the answer. Sonic is another word you hear associated with sound, so you might have heard of like ultrasonic, subsonic, all of those kind of things. Those are all to do with sound waves. Sound is not a transverse wave, it's a longitudinal wave, so it can't be polarized. Okay, so which one of the following statements about stationary waves is true? Particles between adjacent nodes all have the same amplitude. Absolutely they do not. Between two nodes they vary from 0 at the nodes up to a maximum at the antinode. That's not true. Particles between adjacent nodes are all out of phase with each other. Nope, they're all in phase with each other because they all reach their maximum at the same time. Particles immediately on either side of a node are moving opposite directions. That's true, they are. There is a minimum disturbance of the medium at an antinode. No, there's maximum, so it's option C there. Alright, so we've got a double slit interference pattern with fringe spacing W. So we've got all the usual symbols for the different things with a double slit. And what we've got here on the left is the equation that governs a double slit. Which one of these would cause the fringe spacing to still be W? So essentially, whatever you do to the top line, you must do to the bottom line, so they cancel out and give you the same thing. So what I've done is I went down the rows going, what happens to W in each of these cases? So if you double all of them, you'll end up with 2 times the spacing, because the top line is multiplied by 4, the bottom line only by 2. Then B, I went through, actually you end up with just the same thing, so the option is B, but then I checked the other 2 just to make sure I was right, and each of those we ended up with 4 times the fringe spacing, so it's going to be option B there. With these multiple choice, it is always worth checking the other answers as well in case you've made a mistake, so that's what I'll typically do with all of them. Monochromatic light of wavelength 590 nanometers is incident normally on a diffraction grating. We've got the number of lines per meter. We've got an interference pattern. What is the highest order visible? So the highest order visible, we start off by putting sine theta equal to 1, or theta is equal to 90. And so then you can simplify your diffraction grating equation. You should know that D is equal to 1 over n, so that's how I've gone to this equation here. You put the numbers in and you end up with 4.23. So what that tells you is you haven't yet reached the 5th order, so the maximum must be the 4th order. Okay. Which one of the following pairs contains one vector and one scalar? So looking at A, displacement and acceleration are both vectors. B, force is a vector, kinetic energy is a scalar. All forms of energy are scalars, so it's going to be B, but let's check the others. Power is a scalar because it's just energy over time. Speed is a scalar, so they're both scalars. Work is a type of energy, so it's a scalar, and potential energy is a type of energy, so scalar, so it's going to be option B there. Okay, so we've got a uniform square block and it's sliding at uniform speed. So if it's going at uniform speed, we know that the resultant force is 0, or all the forces cancel each other out. So the force used to move the block is 200 newtons, and that must be acting to the right because that's the direction of movement. And then, so you want to work out what the moment of the frictional force is acting on the block about the center of gravity. So if the forward force of 200 newtons is acting to the right, because that's the direction of movement, friction always opposes the movement, so it must be 200 newtons to the left. And friction acts at the point two objects are in contact with each other. So that's going to be in contact with the ground along this line here, so the frictional force has to act somewhere along here, and it has to act to the left. So it wouldn't matter if we put it over on this corner, or in the middle, it's going to be acting to the left. And we can see that that's going to result in a clockwise moment. So it's got to be either A or C, because we can see it's going round clockwise about the center of gravity. Then it's a case of going, well, we know that the magnitude of it, we know its perpendicular distance, giving us a moment of 115 Newton meters. So that's option A. So we've got a perfectly elastic rubber ball, falls vertically from rest and rebounds from the floor. So because it's elastic, we know that it's going to have the same amount of kinetic energy going in as it has coming out. So it's just going to have the same velocity but in opposite direction, the same speed but in opposite direction when it comes off the floor. So which one of the following graphs represents the motion? So if you think about dropping an object, its velocity has to start from 0. So that already eliminates option C, because its velocity is not starting from 0 because you're just dropping it. When it hits the floor, your velocity is going to change direction because it's going to go from being downward to upward. So your velocity should change between being positive and negative at some point, depending on which sign convention you use. But whether you use downward as positive or upward as positive, either way it has to go from being negative to positive. It has to swap over. So it has to go from be D, because both A and B don't show a change of direction. They just show increasing and then decreasing velocity, not a change of direction. So then it leaves it has to be D. So let's do a couple of checks on it. So I said the velocity should be the same but in the opposite direction before and after, so we can see that here that looks like it's about the same. It starts from rest, and then when it bounces it's going to reach the top of the rebound at velocity of 0, so that works. Okay, so we've got a ball projected horizontally from a certain point at the same time as a ball Y, the same diameter, so the same size, but twice the mass, and that is released from rest. And they're allowed to fall vertically from the same height. So they've got the same initial height, they've got the same size, they're going to have the same air resistance even if we were including it, and one's horizontal and one's completely at rest. Which one of the following will occur? So this is a scenario I talked about in class a few weeks ago. Essentially, if you think about it, they both have the same vertical component of velocity, because if one's going horizontally, one's at rest. Both of them have 0 meters per second velocity in the vertical direction to start with. And you should know that the flight time is determined only by the vertical component of velocity. Therefore, if those are the same and they're from the same height, the flight time should be identical. So we can see straight away that's going to eliminate A, because it says the flight time is different, and the same here, same with B, that suggests the flight time is different, but they're not. C, however, says they should be the same, which is correct, because they have the same velocity in the vertical direction and the same displacement in the vertical direction. And then D, again, suggests they hit at different times. Again, that is wrong, so it's left with C. Okay, so take the acceleration due to gravity on Earth as 10, and the acceleration of the moon is 1/6 of that on the Earth, so that gives us a gravitational acceleration of 10 over 6. So we're dropped from rest, and so you want to know what the momentum is after falling for 3 seconds. So we know what the initial velocity is, 0. We know what the acceleration is, minus 10 over 6. So we know what the time is, so 3. So that gives us a final velocity of minus 5 meters per second. So what we need to do is turn that into a momentum. So first thing we need to do is work out what the mass of it is. So if we know the weight force on Earth, and we know the gravitational force on Earth, I think I should actually have used 10, but we'll end up with a number that's close enough. And then that calculates the mass, that's the velocity, and it gives you an overall value of minus 2.5 kilometers per second. If you use the downwards direction as negative, or if you use the downwards as positive, that will give you 2.5 kilograms per second. So it's going to be option A there. Okay. Okay, so we've got a diagram showing the force on a car when it crashes into a wall and doesn't rebound. So we know its velocity becomes 0 if it doesn't rebound during the collision. Okay, so if it becomes stationary, the change in momentum of the object must be equal to the initial momentum of the object. That's how it becomes 0. So the other thing you should need to know is the area under a force time graph represents the change in momentum. So essentially the area has to be equal to the initial momentum, which is A. So A is going to be correct, but let's just check with the others. Momentum is not conserved during the collision. Momentum is always conserved, so that's not right. The momentum of the car might not be conserved, but the total momentum will be. Kinetic energy conserved, we know that's not the case because it's going from having some kinetic energy to not having any, so that's not the case. The average force exerted on the car is 10 times 10 to the 4. No, that's the maximum force you can see here is 10 times 10 to the 4. It's certainly not going to be the average. The average has to be somewhere down around 5, probably slightly less than that. So we know that those are wrong, leaving us with A. Two ice skaters are initially at rest and in contact, and they push off from each other. Which line of this correctly describes what happens to the total momentum and total kinetic energy? So total momentum can never change as long as there's no external force. So the two skaters are part of your system, so any forces they provide are not external forces, so momentum stays the same. So that eliminates C and D straight away. And initially they're stationary, so they have no kinetic energy. They push off, they're traveling at speed, so they have kinetic energy. So the kinetic energy is increased, so we know it's option A there. A stone is projected horizontally by a catapult consisting of two rubber cords. The cords, which obey Hooke's law, are stretched and released. When each cord is extended by x, the stone is projected with a speed v. Okay, assuming the strain energy in the rubber is transferred to the stone, what happens to the stone if each cord is extended by 2x? So what I did was, I thought about, well, if I double the extension, what happens to the amount of energy that I store? Well, if you double extension, the energy is proportional to the extension squared, you're going to have 4 times as much elastic potential energy stored to start with. So that means that you get 4 times as much kinetic energy afterwards. And if you have 4 times the kinetic energy, that means your velocity will be doubled because your energy is proportional to v squared. So if you times kinetic energy by 4, you multiply each of the v's by 2, if you like there. So where a few people got themselves muddled with this, I think, is then they were like, yes, but we've got 2 in parallel to each other, so you'd end up with 4 times the velocity. But that's not exactly the case, because you didn't account for the doubling at any stage here, so you can't account for it at the end. So you could have worked through this and gone with like 2x to 4x if you like, but this is the method that I will use to think about it, which is like, well, if you double the extension, what happens to the energy, and then if that happens to the energy, what happens to the velocity, and that will get you to the correct answer. Okay, the 4 bars A, B, C and D have diameters, lengths and loads shown, and they're all made from the same material. Which bar has the greatest extension? So because they're all made from the same material, they must have the same Young modulus. So what I've done is I've got your equation to calculate the extension here, so that's what you can see down here. So this is the equation to calculate extension, and I've essentially looked at what happens to each of the variables. So I've said for 1, which has just the dimensions L, D and W, I essentially said, let's call that R1. So that's what you can see here. Put 1 for the load, 1 for the length. We know the young modulus is going to be the same for all of them, so you can see there's a 1 in there for that and all of them. And then the cross-section area is dependent on the diameter squared, so I put in 1 squared for that, giving you an extension of 1. If I do that for the second one, so the second one, if we have a look, has 2 times the load, so you can see a 2's gone in on the top line, and it has double the diameter, so you can see 2 squared has gone in the bottom line, so you end up with half the extension, so 1 is still the biggest. We do the same approach for 3, so with 3 the load is 1, so that's why there's a 1 there. Its length is 2, so that's why there's a 2 gone in the top line, and its diameter is double, so that's why a 2 squared has gone in the bottom line. Again, you get a half. And on the last one, you've got 3 times the load, so you get a 3. You've got 2 times the length, so you get a 2 on the top line. Still the same Young modulus, and then 3 times the diameter gives you 3 squared on the bottom line. Overall gives you 2/3, so A is going to have the biggest extension there. And that concludes the multiple choice section of this exam and my review of the mock exam as a whole.